Hello everyone. Today's our objective is to construct a Mohr circle in lecture 5. In lecture 4, I have already discussed about the concept of stress and strain. So I advise you before watching this lecture, you have to go through lecture 4. Okay. So before constructing Mohr circle, we have to know idea about how to write state of stress at a point in general. In general means in three-dimensional space, how to write a state of stress at a point P. Suppose I have taken this as a reference XYZ coordinate system in which this particular three-dimensional body is placed, and due to the action of all these forces F1, F2, F3, F4, suppose the stress generated at this particular point is some sigma resultant sigma R. Okay, so in general, in three-dimensional space, the total number of possible planes will be XY plane, YZ plane and ZX plane. All these three are possible planes. So first, if we are considering XY plane, XY plane will be this one. This one will be the XY plane, that is the board. YZ plane will be this one and ZX plane will be this one. Suppose this XY plane is passing through this particular point, containing this particular point. So the resultant sigma R is something like this one. It is in space because this is a three-dimensional body. So the component of sigma R can be resolved in three components along x-axis, along y-axis and along z-axis. So itself in xy plane there will be three components. Similarly means three stress components in xy plane. Similarly for yz plane, if we are resolving, the component of this sigma resultant will be gives another three stress components, and for zx plane there will be another three stress components. So what will be the actually orientation of these three components? Let's suppose this one xy plane. So for xy plane, the one component will be normal to the xy plane, that is along z axis. Another will be the in xy plane along y axis, and another one will be in xy plane along x axis. So the orientation of these three stress components, one is the perpendicular to xy plane, and the two components, these three components, one stress component is perpendicular to plane and two stress component will be in plane, मतलब plane में होंगे. Similarly there will be one normal component and two in plane stress. Similarly here in zx plane there will be one normal component and two in plane component of stress. So if we draw a parallelepiped which shows all these three components, means there are total 9 components, 9 stress components. If we draw here, let our parallelepiped look like this. Suppose this is x direction, this is y direction, this is z direction, and this is our origin. Okay. यहाँ पे ध्यान देना ये है, how to determine, how to interpret our x plane, y plane, z plane. This plane which is perpendicular to this x axis is x plane. X plane is nothing but the parallel to the yz plane. This will be x plane. Similarly, the plane which is perpendicular to the y direction, this one is y plane, and this one will be, which is perpendicular to the z direction, is the z plane. So this will be z plane, this one. Parallel to the xy plane is z plane, parallel to the zx plane is a y plane. zx plane के parallel ये होगा ना, this one. Okay, so in all x, y, z plane there are three stress component. One is perpendicular, that is along the x-axis. Another one is in this x plane and along the y direction, and another one is in x plane but in z direction. So this component which is perpendicular to the x plane is known as normal components, and these two are shear component, that is component which is lying in this particular plane. So in matrix form we can write it like that: sigma xx, sigma xy, sigma xz, sigma for y plane, sigma yx, sigma yy, and sigma yz, sigma zx, sigma zy, and another one is sigma zz. So ध्यान देना है यहाँ पे, कोई भी एक कंपोनेंट की बात करें, सपोज दिस वन. So in this is sigma xx. The first subscript denotes the plane and the second subscripts denote the direction. I mean to say, the stress is acting on x plane in x direction. For example, what do you mean sigma xz? The stress component which is acting at x plane but in z direction. For example, again sigma zx. This is the stress component at z plane but it is acting in x direction. So let's plot here. So this component will be, this is acting on x plane but in x direction. So this will be sigma xx. This will be the sigma in x plane but in y direction, and this component will be sigma, it is acting on x plane but in z direction. Usually this in plane stress, that is acting along the plane, the stress component which is acting along the plane is known as shear stress component, and it is denoted by not sigma usually, this is denoted by tau xy, but these two terms will be same, that is acting in on x plane, and this will be y direction. So this will be also, this is tau acting on x plane and in z. Similarly, there will be three components on y plane, that is perpendicular to the y plane, that is the normal component, and another two shear components will be on y plane in x direction, on y plane in z direction. So this will be sigma y. Similarly, this will be tau y plane but in x direction. This will be tau y plane but in z direction. Similarly, for z plane, we can show here, one will be normal component, that will be sigma z plane in z direction. Another will be in x direction, that will be in plane acting on z plane in x direction, and another will be acting on z plane but in y direction. So there are total 9 stress components which are required to define a state of stress at a point. Okay, so by observing this matrix, that is the order of 3 cross 3, easily when these two suffix are same, that is xx, yy, zz, so these three stress component will be on normal components, and another 6 components will be shear component. Remaining these 6 components will be shear stress components. Okay, so if we are interested now for a state of a stress at a point but not in 3D, if we are interested to write a state of a stress at a point in 2-dimensional, then what happened? The 2-dimensional state of a stress we can write as xy plane, yz plane or zx plane. Means by vanishing one dimension, either you have to vanish x dimension or y dimension or z dimension. So suppose I am vanishing z dimension. Either we have a freedom to vanish anyone, but generally what we do, we generally vanishes the z dimension. Means every stress component in z direction will vanish, that will be 0. So in this particular matrix, wherever there is a z component, that will be 0. So the 0 will be this one, this containing z, this containing z, this is also containing z, z, z. So our matrix is reduces to only these two cross 2 matrix, and for a state of a stress at a point in 2-dimensional will reduce to a 2-dimensional state of a stress, and it will look like this one, that is sigma xx this will be sigma xx on another parallel plane, this will be sigma yy, this will be sigma yy, and this will be tau xy, another tau xy, and this is clockwise, so there will be complementary shear stress, another tau yx, so this will be, this is clockwise, so this will be anti-clockwise. Okay, so this will be tau yx. Okay. So for two dimensional, the state of stress at a point is reduces to this one, means z कंपोनेंट वाले जितने स्ट्रेस कंपोनेंट है सारे वैनिश कर जाएंगे और हमारे पास ये मिल जाएगा. फॉर एग्जांपल सबसे इंपॉर्टेंट है यहाँ पे ध्यान देना कि ये वाला जो अब प्लेन बचा, दिस वन इज एक्स प्लेन. कैसे पता चला? सी दिस वन इज stress component acting at x plane. First subscript is for x plane and another one is for direction. So at x plane in x direction, this is at x plane but in negative y direction. This one is y plane. y plane में stress कैसे लग रहा है? In y plane but in y direction, that is the normal stress component. And this one is shear stress component at y plane but in this is negative x. Similarly for other two faces. Clear? So easily we can write a state of stress at a point in two-dimensional space. Not two-dimensional space, sorry, in two-dimensional plane. This is the plane stress condition. Okay, I hope now you are ready to specify the location of plane, that is this will be the always x plane. I have already written. This will be the y plane corresponding, this is the another y plane parallel to it, this is another, this is x plane and this one is the another parallel y plane. Okay, so here I want to write again the first subscript 1 and 2 for any stress component. The first subscript is for plane and second subscript for direction. Okay, today for this one only. In the next lecture we will construct a Mohr circle for a plane stress condition, for plane stress condition, that is this one. Okay, thank you very much.